In this lecture, we're going to talk about using the NMOS inverter as an amplifier. So let's assume that you're already familiar with the basic NMOS inverter circuit, which consists of an N-channel MOSFET, a resistor, we'll call it R1, and a power supply VDD, an input voltage, we'll call it Vn, and an output voltage VO. And the transfer characteristic for this circuit looks something like this. So we'll plot VO on the vertical and Vn on the horizontal. This MOSFET, M1, has a threshold voltage. We'll say it's 2 volts. And a transconductance coefficient, K or Kp, equal to we'll say 0.1 amps per volt squared. So here's V threshold. So for input voltages up to V threshold, the transistor is off. We're in pinch-off. Cutoff region. Transistor is off, no current flows, and because no current flows, there's no voltage drop across the resistor, and so the output voltage is just VDD. Okay. Beyond V threshold, the output voltage takes a dive, and it will then eventually leave the saturation mode, which is what's in the middle section here. Saturation. Okay. And it'll go into the triode region, which is to the right of that. And we're not going to worry about that region right now, because as an amplifier we want to use the circuit right in that transition region where the slope is steep. So we want to position ourselves, let's say, right around here, which is perhaps at about 0.5 VDD, right? And we want to consider what happens if we apply an input voltage, I'll call it VGS, big capital V, capital G, capital S, all right? And that'll lead to a corresponding capital V, capital O output. And if we set up that DC input voltage and then we apply superimposed on that an AC voltage, sinusoidal, let's say it's sinusoidal, but it could be any kind of AC voltage, how does the output vary? Okay, so one way we can draw this, let me redraw this curve here, and let's see, so this is Vn. Now if we have an input that varies around some operating point, V, capital VGS, okay, then the output would vary in a manner similar, but it would be scaled by the slope of that curve. So this right here is Vn, and this would be V out. Now let me draw this one more time. If we zoomed in and we had a real steep slope, okay, on our curve, and if we put in an input signal that varies by that amount indicated, we would find that the output would vary by a larger amount, and that is because this slope, the slope here is, or the magnitude of the slope is greater than 1. So we get amplification. So a small change in the input produces a larger change in the output. And that's how we want to use this circuit as an amplifier. So we want to actually analyze the circuit and determine exactly how much amplification we're expecting. So recall that in saturation we had IDS is equal to K over 2, or Kp, I'm just going to say K, we'll cross out the P there, keep it simple, K over 2 VGS minus V threshold squared. Okay, so this looks like a square law curve. VGS, IDS. Okay, and we can look at okay, so we have that. We've modeled this as a current source, right? We've modeled it as a current source. So let's redraw our circuit where we're going to replace our transistor with this K over 2 VGS minus V threshold quantity squared. Okay, this voltage V out is going to be equal to VDD minus R1 times IDS. Okay, and IDS is going to be equal to K over 2 VGS minus V threshold squared. Now we can determine the slope of our output transfer curve directly, but let's first look at the slope of our IDS versus VGS curve. Okay, so the slope at this point here, which is at some capital I, capital D, and capital V, capital GS, this slope is equal to dIDS with respect to dVGS evaluated at big VGS, comma big IDS. Right? So what is that? The derivative of IDS with respect to VGS is going to be equal to just K over 2 times K over 2, so it'll be K times VGS minus V threshold to the first power. Okay. Now we also know that, well, looking at the expression right here, we can express this VGS minus V threshold as 2 IDS over K square root of that. Okay, so we can write this, if we pull the K, this K here in, we can write this is equal to 2K times IDS. Okay, so that's an equivalent form. So the slope of the curve is square root of 2K IDS, and it's also equal to K times VGS minus V threshold. Now notice that these are capital IDS, capital VGS. All right, those are the operating points where you're sitting on the curve. Now we give this actually a name. We call this GM. Okay, and this is the transconductance. The small signal transconductance, I guess we say small signal transconductance. Meaning that if you're only changing the input voltage a small amount, VGS a tiny bit, you'll get a tiny change in IDS and it will be linearly related. If you stay in that small signal region, it'll be a linear relationship, and the linear relationship will be determined by GM. So we could write therefore a small change. Let's say if VGS is equal to big capital VGS plus some small signal VGS, I'll put a little tilde over that, okay, then we can say that IDS is going to be equal to some big IDS, capital I, capital DS, plus some small signal IDS, where little IDS is going to be equal to GM. I'll say approximately. It's actually approximately a GM times little VGS. All right. So small signal wise, we have that little IDS is equal to GM times little VGS, where GM will be evaluated according to where we are as an operating point on that curve. So we can either use the square root of 2K times capital IDS, or we can use K times capital VGS minus V threshold. Okay, so now we can use this and return to our circuit. We can take this right here and we can redraw our circuit to use a linearized current source. We can say this is GM times VGS, little VGS. Okay, and what I'm going to do now is we're going to remove all of the all the DC signals, and we're going to turn them off, and we're going to leave only the small signals, the small AC signals there. So notice that capital VDD, the power supply, has been turned to 0. It has no small signal variation. It's a DC value, so we're going to remove it. We've removed the capital VGS and we've removed the capital IDS, and all we will have here is small little VO. Okay, now little VO can be written very easily now in terms of little VGS. It is simply the current flowing through R1 with a minus sign because of the polarity there. So it's minus R1 times little IDS, which is simply minus R1 times GM times VGS, little VGS. Okay, this minus R1 GM is the small signal gain. Okay, now maybe this confused you how I did this, so let's go back to this expression here. Okay, that comes straight from our large signal analysis that we did in a previous lecture when the inverter was operating in the saturation mode. So what we can do is we can write VO, let me rewrite that, VO equal big VDD minus R1 K over 2 VGS minus V threshold squared. Now, if we want to know what the small signal gain is of this amplifier, remember we wanted the slope back here, we need to take the derivative of VO with respect to VGS, or Vn. All right, Vn is the same as VGS. So let's do that. When you take the derivative, the first term goes to 0. We'll end up with minus R1 times 2 times K over 2 times VGS minus V threshold. All right, and this will become minus R1 times K times, and we need to evaluate this at a VGS equal to capital VGS, right, at our operating point. So this will be capital VGS minus V threshold. We recognize that this term here is simply our term for GM that we had defined above. So therefore, we again have that the derivative of VO with respect to VGS or Vn is minus R1 GM. Right? So therefore, so we can equate essentially DVO as being the same as little or small signal VO, okay, and DVGS as our little small signal tilde VGS. So this leads us to writing small signal VO is equal to minus R1 GM times small signal VGS. So that's our slope. So let's work an example here, or that's our gain, I'm sorry. Suppose, well, we had some values up here, right? We didn't define R1. Let's say R1 was equal to 1 kilo ohm. Okay? So suppose VO, big VO, was equal to 1/2 VDD. So, and VDD was equal to 5 volts. Okay, so that means that VO is equal to 2.5 volts. It also means that the current IDS, operating point current, is going to be equal to VDD minus VO over R1, right? And that's going to be 5 volts minus 2.5 over 1K, which is 2.5 volts over 1K, or 2.5 milliamps. Okay, so based on that, we can calculate GM as being square root of 2 times, what did we say K was? 0.1. 2 times 0.1 times 2.5 milliamps. Okay, and that's equal to 22.4 milliamps per volt. Okay, so now we can say, therefore, VO, little VO, with respect to little VN, or little VGS, is equal to minus R1 GM, which is going to be minus 1 kiloohm times 22.4 milliamps per volt, which the millis and the kilos will cancel out and end up with minus 22.4 volts per volt. All right, so this is our small signal voltage gain. Okay, so let's apply that. Suppose we have a VN that equals some capital VGS plus 10 millivolts times a sine omega t, whatever omega is, some frequency. All right, and VGS is chosen, so VO, big VO, the operating point, is equal to 1/2 of VDD. And we'll say find the small signal output VO, little VO. So, find little VO, and then let's also find the big VGS that's needed. Okay, well, we already found that, so previously we found that IDS was equal to VDD minus big VO over R1, which we found to be 2.5 milliamps, right? And so IDS, which is equal to K over 2 VGS minus V threshold squared, we can solve for VGS here, right? VGS, big VGS, is going to be equal to, let's say, square root of 2 IDS over K plus V threshold. Okay, so that'll be square root of 5 milliamps divided by 0.1 amps per volt squared plus, we said 2 volts. So what does that equal? 2.22 volts. Okay, so therefore, big VGS equal to 2.22 volts leads to big VO being equal to 5 volts over 2 as prescribed. Okay. Previously, we also found that little VO with respect to little VN was minus 22.4 volts per volt times little VN. Okay? So therefore, we would have at the input 2.22 volts, and we're going to put in a sine wave that's superimposed on that. Very difficult to see because it's so small, right? So this peak-to-peak amplitude is going to be 2 times 10 millivolts. Okay, this right here is Vn of t. We'll put that in our amplifier. I'll draw this as an amplifier like this. And it has a small signal gain of minus 22.4. Okay, and this is powered to VDD. And what do we get? So this is Vn, and what we get at the output is something that is sitting at 2.5 volts, okay, and we'll have the opposite sign, okay, where this will be the peak-to-peak here will not be 2 times 10, but it'll be 2 times 224 millivolts. Okay, so that's what this amplifier does. It takes in a small signal and amplifies it, and of course the whole what determines the gain, the small signal gain, is going to be dependent on where you bias the circuit. So if we were to, for instance, bias the circuit such that the operating point output voltage, big VO, was, say, up at 4 volts rather than being at 2.5 volts, the slope there is shallower, right? So we have this is Vn and VO. The slope up there is shallower than what it is right here. So if we were to set up our operating point up here at 4 volts rather than right here at 2.5, we would say that the small signal gain is smaller, is lower compared to the gain at big VO equal 2.5 volts. All right, so it's important. We have to know the operating point before we can determine the small signal gain. Okay. Now, a trade-off would be also, you could say, well, if we made it down at say 1 volt, okay, the gain here is larger. Right? This is a square law. So since there's a square term, the higher the current is, the lower the output voltage, right? Because it's VDD minus R1 times IDS. So the higher the current, the greater the slope in the transfer characteristic. This is VGS and IDS. Right? So up here, the slope is steeper than what it is right here. So operating down here at 1 volt output voltage, where you're running at a higher current, would actually give you a greater gain. However, you're closer to bottoming out. Right? So you have a limited output voltage range before the amplifier clips, as we might call it. It clips low or it clips high. And so, although you can get more gain there, you can't have as much of a signal swing in the output. So you're better off oftentimes having it more near the center, where we have chosen it to be there at half of VDD.